My presentation is using mathematics to help cure hunger, disease, and global warming. Well, despite the hyperbolic title, we're only going to be looking at parabolas. In fact, we're going to look at the mathematics of solar cookers. Now, solar reflectors are quite a hot topic these days. This is a picture of the Solar One power plant in Nevada, a parabolic trough solar concentrator concentrates the sun onto a narrow pipe full of fluid which is heated, passed through multiple such concentrators, and then used in a heat exchanger to convert water to steam, and the steam is used to run a conventional steam powered generator. And that's what the whole thing looks like from the air. Here's a different style of solar concentrator. This time this is not obviously functioning, it's not pointing at the sun, and this one particular one I think is in Spain. Here are some backyard solar concentrators which are used to cook dinner in some high altitude, high sunlight, low wood parts of the world. And here is the Kyoto Box, a very simple solar concentrator which actually won $75,000 in the Financial Times HP Climate Change Challenge. So we've seen some parabolic reflectors along with our box. We're going to look at a problem involving a box and a problem later involving a parabola. Why a parabola? Well, the reason a parabola is used is the focal property of the parabola, which says that any ray of light coming in parallel to the axis of the parabola reflects through its focus. What's the converse to that property? The converse, of course, is that any ray that comes in not parallel to the axis misses the focus. The converse is in fact true. So what that says is if you're not pointing directly at the sun, and you have a very small target at the focus, the parabola is a very bad shape. So you have a couple of choices. One, your target has to be moderately big, so it's tolerant to change in direction of the sunlight, or you have to keep repositioning the parabola to track the sun. And that's something we're going to look at in the second part of this talk. The first part, however, we're going to look at a very simple solar concentrator consisting of just a box with a reflective lid, and we're going to ask what angle should that lid be open to. In the second part, we're going to ask ourselves what shape of parabolic mirror has to be repositioned least often. We're going to use geometry expressions, and we're going to use an algebra system. In this talk we'll use TI Inspire. So the first question, what angle should the lid be open to? Let's assume that the sun is coming in from a given angle. Then what is the best angle to open the lid of this box? Think about that and see if you can guess the answer for, let's imagine, for example, the sun is coming in vertically. What angle do you think the box should be open to? Or let's take another example. Here in Oregon, the sun is at the equinox. The sun will come in at 45 degrees. So imagine the sun is coming in at 45 degrees. What angle would you guess the box would be open to? Well, let's see if your guesses are right. We're going to model the general situation in geometry expressions. So first of all, I'll create the lid of my box, the top of the box, and the box lid. I don't really need my axes anymore. I can create to have a nice visual effect. I'll actually make the box here. I would like the lid of the box to be the same size as the top of the box. It's just a closing box lid, so I'll make the two things congruent. And I would like the let me just constrain the size of the top of the box to be A. I don't need this. And I will lock A. And that means that if I move the box lid, it's going to do the right kind of thing. So let's me model a ray of sunlight by an infinite line here, just to reinforce the fact that it's sunlight. Let's change its color. We'll have a kind of orange evening sunlight here. And then if I reflect that, and let's specify its angle. So it's coming in at angle theta to the top of the box. So if we can now reflect that ray of light in the lid of the box and see where it goes. And we can look and see what would be a good angle for the box lid. Now we can see that the various different rays of light that hit the box lid, we can see where they're going to reflect to. Clearly, no matter where the box lid is, at the very inside it's going to reflect into the box, and as we go out somewhere along the line we're going to start losing light. This doesn't look like a very good angle for this for the box lid, given the angle theta that we have for the incoming light. Let's try a different one. We'll close the box lid a little bit, and we can see, okay, we're getting much more of the light, but we're still losing some. Now we can see that really the important place to look is at the exact outside of the lid. Everything towards the hinge from there is going to reflect in again towards the hinge on the box. So really the important one is the ray of light which goes through the very edge of the box. And we could relatively easily convince ourselves that if the box is too far open, we're going to lose a significant amount of our light. If it's too closed, sure, we'll capture all the light, but we could have captured more if we'd opened it a bit more. And in fact, it's reasonably easy to convince ourselves that what we'd like is for the reflected ray to go through the corner of the box B. So how can we make that happen? Well, let's put an angle phi for the box lid, and we can ask geometry expressions what are the other angles in the system. Here we see that angle. There is phi minus theta, and we can see this angle here is 180 plus theta minus 2 phi. Now, if we wanted to see how we could work out these quantities by hand, well, we could see, okay, let's look at this angle here. That's not the one we would like. We'd like that angle there. Oh, yeah, that's 180 minus phi. That makes sense. That angle's theta. So what's this angle up here? Oh, indeed, phi minus theta. 180 minus the sum of these two angles. And of course, because this is a reflection, this angle here equals this angle here. And we get phi minus theta. And then we can see, okay, phi, that's 2 phi minus theta, and we have to subtract that from 180 to get this angle. So yes, we could have worked all that out by hand. However, if we want the situation where the reflected ray goes through B, what we would like is for z1 to equal z0. In other words, we'd like to arrange phi so that the equation phi minus theta equals 180 plus theta minus 2 phi is solved. So how would we solve that? Well, let's look at this side of the equation. It's got minus 2 phi on this side, is a phi on that side. So let's bring that over there, and we'll get 3 phi on that side of the equation. So 3 phi equals 180 plus, then there's a theta there, bring that over to this side of the equation, 180 plus 2 theta. So phi would have to be a third of 180, which is 60, plus 2/3 of theta. So 60 plus 2/3 of theta. Let's try that. (60 plus 2 times theta upon 3). And sure enough, we see that the two angles are the same. That one's 60 minus theta upon 3, that one's 60 minus theta upon 3. This is an isosceles triangle, so this line, the reflected line, is indeed going through B. So okay, I gave you a couple of things to think about. First of all, what if theta was 90 degrees, so if the sun was coming in directly? Then this angle 60 plus 2 theta upon 3, that'd be 60 plus 2 times 90 upon 3, or 60 plus 60, which is 120 degrees. Did you get that right? The other situation was when theta was 45. Let's put that into here. In that case, 2/3 of 45 is 30, so 60 plus 30 is 90. So in the case where the sun is at 45 degrees, the angle should be 90.